Hello, Physics 20s. In today's lesson, we are going to talk about the forces that are responsible for uniform circular motion, which is called a centripetal force. And more specifically, we are going to, one, explain qualitatively uniform circular motion in terms of Newton's laws of motion. We're going to look at the first and second law more specifically. And two, apply Newton's laws of motion to solve algebraically linear motion problems in horizontal and vertical planes near the surface of the Earth, ignoring air resistance. We've seen that learning outcome before, and it just means we're going to apply our problem-solving procedure for dynamics, where we draw free body mass acceleration diagrams, write equations of motion to mathematically model the problem, and then solve for unknown information. We can use that same procedure for problems involving forces with circular motion. So we're going to start off by talking about a centripetal force, which I'm going to use the variable sigma Fc to represent. The sigma is an indication that this force is going to be a net or an unbalanced force. Going back to the last lesson, we talked about the centripetal acceleration of an object in circular motion. And that centripetal acceleration, the word centripetal itself means center seeking, is always towards the center of the circle. Doesn't matter where we are in uniform circular motion, our centripetal acceleration always points towards the center. If we go back to Newton's second law of motion, Newton's second law of motion tells us that if we have an unbalanced force in one direction, there must be acceleration in that exact same direction. So if we write down Newton's second law of motion in a mathematical format, we know that equation is sigma F is equal to mass times acceleration. If you have a net force that is, for example, towards the left, then that means your acceleration is also towards the left. Now we can work backwards in terms of uniform circular motion. If we know that our acceleration is towards the center of the circle, then that tells us we must have a net or an unbalanced force that is also going to be towards the center. We call this net or unbalanced force a centripetal force. And again, centripetal because it's a center-seeking force. It's always going to point towards the center of the circle. And we can actually calculate this force using the equation for Newton's second law of motion. What I have is sigma Fc is equal to mac. So the only difference between this equation and the way I wrote down Newton's second law of motion in the dynamics unit is I changed the subscript attached to the F and the A. I've put the subscript C here. The C just means we're looking at a center-seeking net force and center-seeking acceleration. We'll get into the examples in a moment. The only real difference is going to be that we now have an additional equation we can plug in for acceleration. I shouldn't say an additional equation. There's one equation we can plug in for centripetal acceleration, which is your acceleration is either your speed squared divided by r, or 4 pi squared r over t squared. This is a key physics principle that is found on the formula sheet. I believe physics principle number 2 is uniform circular motion, and then in brackets it clarifies what direction the net force is. Radially inward just means that the force points towards the center of the circle. Now, I should point out that the centripetal force is not a new force. What I mean by this is when we look at objects and draw a free body diagram, we're not going to write down sigma Fc on the free body diagram. The 4 main forces we've talked about so far, that being the gravitational force, the normal force, the applied force, and the frictional force, they will all behave like a centripetal force in a specific scenario. So let's look at a few examples of when those four forces would actually be a center-seeking force that is responsible for uniform circular motion. Starting with an applied force. Well, the main example I looked at last time was we had that rubber stopper and we were spinning the rubber stopper around in a circle. So I believe I had, again, the little crosshair symbol means the center of the circle. I had a little rubber stopper and we were spinning that rubber stopper around in a circle. In this case, if you drew a free body diagram of this object, the centripetal force would be, there's that tension in the string, and that string would be exerting an applied force on the object that would point towards the center of the circle, no matter where you are. So that's one example of where an applied force could behave like a centripetal force. Tension in a string attached to a swinging rubber stopper. If you don't have the tension in the string, the object can't go in a circle anymore. For example, if you cut the string and then you eliminate the tension, that rubber stopper is going to leave the circle. 2, the force of friction. Well, let's say that you are driving and you want to make a turn on a road. Here's my road and I want to make the turn. Now let's draw a box to represent the car. Here's the center of the circle. You need friction between the road and the tires for you to go towards the, go towards the center of the circle, but for your trajectory to eventually change those towards the center of the circle. So I need a frictional force that's directed towards the center. Now, think about what would happen if you did not have this frictional force. If you did not have this frictional force, this could be the case where it's super icy outside and you do not have enough friction between the tires and the road. What would happen is, well, whatever your inertia is, so at this point here, your velocity is tangent to the circle. Without that frictional force that supplies the acceleration, if it was really, really icy and you had no friction, you just keep moving in a straight line. You just keep doing what you're doing. Your inertia just wants you to keep going in a straight line. So I do need the frictional force directed towards the center so it can eventually change my velocity so that when I'm at the top of the turn, I'm then pointing towards the left from this perspective. So in this case, the force of friction, which prevents a vehicle from sliding off the road when making a turn around a corner, it is behaving like a centripetal force. Gravitational force. Well, we could look at the Earth. And then we have a satellite going around the Earth. We could use the moon. I'll just put M for moon. Roughly circular orbit around the Earth. And we would need the force of gravity acting on the moon, directed towards the center of the Earth, in order for the moon to continue to move in a circle. So in this case, the gravitational force keeps satellites in orbit around the Earth, and satellites can include the moon. 4, the normal force. Think about you have a loop-de-loop. There could be a roller coaster track where you're going around a big loop. And maybe at the very top, the roller coaster cart is upside down. And the center of your circle would be here. So what you'd have is the roller coaster cart would exert a force on the track. In return, the track would exert this equal and opposite reaction force, which would be a normal force back on the roller coaster cart. this force would be directed towards the center of the circle. Obviously, if you didn't have the track, then the roller coaster cart would just fly off. So you do need the normal force from the track on the cart to act as a centripetal force. There's one other force I want to talk about, but mainly just to clarify that this is not actually a real force. In fact, people use this force a lot, thinking that it actually does exist, but it does not. So I'm going to go through the misconception of what a centrifugal force is. All right, I have a little animation to illustrate this point. So what this animation shows is we have, like, say you're sitting in a car. I have my passenger view. So that's just me sitting in my seat and I'm looking forward. And then I also have a bird's eye view in terms of what's going on. So the bird's eye view would just be a top view perspective of the car as it's going around in a circle. All right. All right, so I want to get the animation going again. All right, so when you look at this vehicle that's going around in a circle, you might have noticed that if you have like an object on the dashboard, that it seems like there is a force that is pushing your object on the dashboard in a way so it's almost like leaving the circle. So in this case, if I try to draw this, so we have a tape that's on top of the actual dashboard. As I make my turn, it seems like there is some kind of force that is acting on the tape and it is pushing it towards the right. And what that force seemingly is trying to do is, while the rest of the car is turning around, that force seems like it's trying to get the tape to escape the circle. So that's what we call a centrifugal force. Centri means center. The fugal part of that word means fleeing. So it seems like there's a force that's trying to get you to leave the circle. In fact, even if you're in the car seat and like you make like a really, really sharp turn, it almost seems like you're being like pushed like outward against the door. So in that case, it seems like there's some kind of centrifugal force that's trying to get you to once again flee the circle. Now, here's a reason why this is not actually a force. So the centrifugal force seems to be some kind of a force that is causing an object to escape moving in a circle. And if you look at the actual motion of the object as it tries to escape the circle, it just moves in a straight line. So this is where you need to look at the bird's eye view. So I'll pause this in a second where I can kind of just show like what's going on at the actual tape. Okay, let's do it at this point. So these little small little rectangles, it's just showing like the position of the tape as the car is making the turn. All that's happening is this tape that's on your dashboard, it's simply just trying to go in a straight line. In fact, that's what the inertia of the object is. The inertia of this tape is it just wants to keep doing what it's doing. So it's moving forward at a constant velocity, and it just wants to keep moving forward at a constant velocity. Now, here's why the force doesn't actually exist. Newton's first law of motion simply tells me that if an object's at rest, it'll stay at rest. Or if an object's moving at a constant velocity, it will continue moving at a constant velocity until you subject it to a net force. So in this case, again, I'll stop the animation in a moment. So what's happening is as the car makes the turn, all this tape is trying to do is just, it's moving at a constant velocity and it just wants to continue moving at a constant velocity. You don't need a net force to do this. That's just the inertia of the object. It's its tendency to keep moving in a straight line. So what's happening is the rest of the car is being subjected to a centripetal force. So the centripetal force on the car would be a frictional force that's pointing towards the center of the circle. But the tape on the deck, it just continues to try moving at a constant velocity. So it's inertia's, whatever it's doing, it wants to keep doing it. And again, according to Newton's first law, I don't need a net force to do that. I need a net force to change its velocity. Therefore, there is no such thing as this center fleeing force. It's just weird because when we're inside the car, from our perspective, it seems like we're stationary as we're making the turn. And it seems like something is like pushing on that tape and moving it towards the right. But there is no force moving it towards it on the right. It's just that our position in the car is changing and the tape is just trying to continue to move straight forward. And what that appears like from our perspective is the tape just keeps moving towards the right side of our dashboard as the car starts to make that turn towards the left. So again, just be careful in how you use these words in, I don't want to say in everyday life, because I'm sure most people don't care, but I do find a lot of people do use the word like centrifugal force compared to centripetal force. The centripetal force is the one that gets you to move in a circle. The centrifugal force, well, there is no centrifugal force. It's just simply your inertia that's just getting you to keep doing whatever it is you're doing. And in this case here, just wants the tape on the dashboard to continue moving in a straight line at a constant velocity. All right, so let's go through a couple of examples now, where we're going to start to apply a very similar problem-solving procedure as we've done before. So first one, I have a 2 kilogram mass is tied to the end of a string and is whirled in a horizontal circle with a radius of 5.0 meters. It tells me that the frequency of this rotation is 6.0 hertz, and I want to calculate two things: the speed of the mass and the magnitude of the tension in the string. Okay, so we could actually do the calculation A from last time. We don't need any additional information to do it, so let's start off with part A. First things first, usually if we have we're given the frequency, we typically want to convert that into period because we see the period variable in most of our equations. So I'll do that. I know that the period is equal to 1 divided by my frequency, which would be T is equal to 1 divided by 6.0 hertz. 1 divided by 6 would be, and let's give one extra significant digit for an intermediate calculation, to be 0.167 seconds. To calculate the speed of the mass, we can use the equation Vc is equal to 2 pi r divided by the period. I know on the formula sheet it shows it as the magnitude Vc, but I could just simply drop the vector and the magnitude sign and just write down Vc to indicate the speed. It just saves a little bit of work. Okay, plug the numbers in. So this would be 2 pi times r the radius, 5.0 meters. Capital T, which is my calculated period, which is 0.167 seconds. And I get Vc is equal to, we're going to two significant digits, and I get 1.9 times 10 squared meters per second. So far, nothing different in comparison to the calculations from the last lesson. B wants me to calculate a force, and to do this, we're going to use the exact same procedure we used for all our dynamics problems in the previous units. We'll start off with the free body diagram. Free body diagram. Now, it says it's whirled in a horizontal circle. When I say a horizontal circle, it means it's being rotated in a direction that is parallel to the ground. horizontal circle parallel to the ground. We're going to draw a bird's eye view, which means like a top view perspective of what the rubber stopper would look like. Well, it says a mass here, whatever. It could be a rubber stopper. Okay, so in the free body diagram, I'm going to put this plus or this crosshair symbol to indicate the center of the circle. And then I'm going to draw my mass at one end. What I'm also going to do, and I'll do this in a different color, is I'm just going to show what the trajectory of the object looks like. So now this shouldn't actually be part of a free body diagram, which is why I'm drawing the circle with a dashed line. So it just shows like what the trajectory would look like if this rubber stopper went through one complete revolution. Now, before I fill this in, I'm going to draw the MAD. Here's my rubber stopper, my mass, M, center of the circle. And then let's just draw the trajectory of the object. Do as a dashed line, because technically it's not supposed to be part of an FBD. And I'm going to draw the acceleration. I find starting at the MAD is helpful in getting the direction of your forces correct. All right, we know that an object in uniform circular motion, the centripetal acceleration is always going to point towards the center of the circle. So we're going to call that AC for your centripetal acceleration. What Newton's second law of motion tells you is that if you have a acceleration towards the center of the circle, there must be a net force towards the center of the circle. That's your centripetal force. The question here is, well, what is the centripetal force? Well, the centripetal force is just the tension in the string. So the tension in the string, if you envision yourself as the rubber stopper, you'd feel the pull of the string towards the center of the circle. So we'll call that FA. By the way, it doesn't matter where you draw the object. You could have drawn at the top, the right side, the bottom. It makes no difference in terms of how we derive the equation of motion for a horizontal circle anyways. Okay, so let's start off with our circular motion physics principle. So I'm going to clarify, I want right to be positive, and I'm going to look at the sum of my centripetal forces, and that is equal to mass times centripetal acceleration. And that's your uniform circular motion physics principle. Okay, so what this means is look at the FBD, look at all forces in this centripetal direction. If it points right, it's positive, left, negative. Well, it's not even a sum. There's one force, it's the applied force, and it points towards the right. So you have FA. This would be equal to M times, well, the acceleration is also towards the right, so it would be MAC. Now, the extra thing I can do for a circular motion question is I have an equation equations I can plug in for the centripetal acceleration. One equation is useful if you know the speed. One equation is useful if you know what the period is. In this case, well, we just calculated the speed, so let's use the equation that has speed in it. So what I want to do is, in the place of AC, I'm going to plug in this equation. AC is equal to VC squared divided by R. Once again, the formula sheet it says the magnitude of the vector. If I just write down AC without a vector sign, it just implies its magnitude. So now I would have FA is equal to mv squared divided by R. And I can plug numbers into the equation now to calculate this. So this would be 2.00 kilograms multiplied by the speed. Well, the speed we got from part A, so that was 1.9 times 10 squared meters per second, all squared. Divide this by R, which is the radius, 5.0 meters. And if I plug these numbers in, we're going to two significant digits. I should get the magnitude of my applied force as 1.4 times 10 to the power of 4 newtons. For part B, it's just like solving a regular dynamics problem. The only difference was that I had an extra equation I could plug in for acceleration. Otherwise, the problem-solving procedure is identical. So let's apply this to the next example. Example 2. I have a 1,000-kilogram car that rounds an unbanked curve. Unbanked curve just means that there's a turn, but it's on like a flat road. There's no incline of the actual turn. The radius is 80 meters. Tells me the coefficient of static friction between the pavement and the car tires as 0.51. And then I want to figure out the maximum speed the car can make the turn without leaving the circle. Okay, so let's start off once again with the free body diagram. Now, this time I'm going to do it from a side view perspective of the car. So I'll do FBD. Instead from a top view perspective, I'll do a side view. Okay, so here's the center of the circle. Here is my object. We'll do the MAD first. So here's my object, mass M, center of the circle, and my centripetal acceleration, AC, would be towards the center. There's no reason to draw the trajectory of the circle because it's not in the plane that we're actually looking at the diagrams in. The plane of the circle trajectory would actually be cutting into the page or into the screen. Okay, let's fill in the free body diagram. So from a side view perspective, I would have the force of gravity that's straight down. We'll call that Fg. Because I have no acceleration in the vertical direction, I would have my normal force from the ground that points straight up, and it's going to be equal and opposite in magnitude. Now, in terms of, well, what other force is acting on this object, the car? Well, it's friction. Friction is a thing that's allowing me to make the turn. What direction does the friction force point? Well, the frictional force is the centripetal force. The centripetal force is towards the center of the circle, which means that the frictional force, which is the centripetal force, must also be towards the center. Without that frictional force, I cannot move in a circle. You would actually just leave the circle in a direction tangent to the circle at that point. Okay, so what we have here is we have two planes we can deal with, like a vertical plane and a horizontal plane. So I'm going to start in the vertical plane just to derive a really simple equation. So we'll start off with, let's assume up is positive. I'm going to find the sum of the forces in the y direction. There is no acceleration in the y direction. That's equal to 0, which tells me my physics principle, which is that the forces are balanced. Let's expand this. Fn points up, it's positive. Fg points down, it's negative. So I have Fn minus Fg equals 0. We can expand Fg. So I'd have Fn minus m times g is equal to 0. And this would tell me that Fn is equal to mg. If I wanted to at this stage, I could plug in the mass and plug in the acceleration due to gravity, but I'm not going to do that because I'm going to show you what happens if you just keep everything in terms of variables. I'm just going to box this equation and call it equation 1. So in this situation, the normal force is just equal to the mass of the object times the acceleration due to gravity magnitude. Okay, now let's go to our centripetal direction. So my centripetal direction towards the center of the circle, so I have the sum of the forces in the centripetal direction, would be equal to mass times acceleration in the centripetal direction. Because I'm dealing with centripetal force and acceleration, the physics principle is called uniform circular motion. Yes, the forces are unbalanced, but we can be more specific because we're dealing with circular motion. So uniform circular motion. Let's expand this. Okay, there's only one force that makes up the centripetal force. It's the force of friction. It's going to point towards the right, therefore it's positive. So you'd have FF is equal to M times the acceleration is also positive times AC. Force of friction. Now it says, what's the maximum speed the car can travel around the circle? Well, the maximum speed the car can travel around the circle would be, I would need to maximize my static friction. So if we're dealing with a maximum point for static friction, we can actually plug in the equation, mu s times Fn. And that would be equal to m times centripetal acceleration. The equation we're going to plug in right here is the one from the previous slide. So the centripetal acceleration in terms of the speed, because that's what we want to calculate, is v squared over r. So we plug in v squared over r for the centripetal acceleration. What I'm going to do is I'm going to make a quick substitution. So I'm going to take equation 1, and I'm just going to plug it in for Fn. If I plug it in for Fn, I would then have mu s times mg is equal to mv squared divided by r. Now here's the reason I did not calculate the normal force. You'll find oftentimes in a physics problem, if you just carry variables as long as possible, things are eventually going to cancel off. If I divided both sides of the equation by the mass, they would cancel off. So even though I gave the mass in this question, we don't actually need to use the numerical value. Now, if you did calculate the normal force initially, you would need to use it, but I chose to keep it in terms of variables, hoping that things would cancel off, and they did. Okay, we want to get the speed by itself. So to do that, all we have to do is multiply both sides of the equation by r and then take the square root. So this would then turn into v is equal to mu s r times g. Let's should put the c here. Speed in circular motion. So vc would then be equal to the square root of my coefficient of static friction, which is 0.51, multiplied by r, which is 80 meters, multiplied by g, 9.81 meters per second squared. And then, if we calculate this, I got a number to 2 significant digits. That is 20 meters per second. Now, some of you might be wondering, why is it static friction? Because we have a moving car. Like if a car is moving and there's friction that's opposing it, should it not be kinetic friction? Well, this is a little bit complicated to explain. To properly explain it, we need to look at the physics behind rolling motion, which actually is something we deal with in the AP portion of Physics 20. I'll give like a bit of a loose, not totally accurate explanation here. I mean, this is not the correct reason for why it's static friction, but maybe for now it can satisfy you for the time being. Okay, let's say we looked at a bird's eye view perspective of the car. Then drew like the circle. To represent it. Again, this is not the correct way to justify it, but maybe the way I would justify it is if you look at the distance between the car and the center of the circle, which is the radius, it doesn't matter where you are, the radius is not changing. So I suppose from the perspective of the radius, the center of the circle, it seems like the position of the object is not changing. And if your object is not really changing or moving from that perspective, I suppose we could look at it as static friction. But again, this is not the correct explanation as to why is static friction. Again, there is an AP lesson on rolling motion where we talk about this in more detail. It's just our mathematical model at this point of our objects is not good enough to explain why it is static friction. Anyhow, for regular physics 20, it's not something we need to worry about, but it is static friction in this situation. Okay, so that concludes the lesson where we talked about how the different types of centripetal forces responsible behind the motion, and you can complete the assignment called centripetal forces. And in the next lesson, we'll just look at some more complicated examples of applying all the work that we talked about today.